NGC 6946, often called the Fireworks Galaxy, lies at the border between the constellations Cepheus and Cygnus, roughly 22 million light-years away. Though modest in size compared to grand spirals like Andromeda, it boasts an exceptional record of stellar cataclysms. Over the past century, it has produced at least 10 observed supernovae, far more than the Milky Way in the same time, earning it its explosive nickname. This high rate of supernova activity is not random. NGC 6946 is a starburst galaxy, meaning it forms stars at a dramatically elevated pace. Its rich interstellar medium is packed with cold molecular clouds, which collapse under their own gravity to give birth to new suns. Many of these stars are massive and short-lived, burning through their nuclear fuel quickly before exploding as supernovae and seeding the galaxy with heavy elements. Its structure reveals tight spiral arms filled with pinkish hydrogen emission regions, H2 regions, glowing from the ultraviolet radiation of newborn stars. These regions are teeming with protostars and stellar nurseries, each one a pocket of cosmic creation. The galaxy's dust lanes, visible in infrared observations, weave through the disk, obscuring and sculpting the view like shadowed brushstrokes on a galactic canvas. In multi-wavelength imaging, from radio to X-rays, this celestial system appears as a chaotic yet harmonious symphony of gas flows, magnetic fields, and stellar winds. Embedded in the core lies a region of intense star formation, radiating not just invisible light but powerfully in the far infrared, suggesting vigorous heat from dust warmed by ultraviolet radiation. Unlike many grand design spirals, this stellar structure lacks a sharply defined bulge or prominent bar. Instead, its central zone is soft, turbulent, and asymmetrical, possibly the result of past minor mergers or gravitational interactions with smaller companions now dissolved into its halo. Studies have revealed unusually strong magnetic fields that help shape the motion of gas and regulate stellar birth. These fields, mapped through polarized radio waves, thread through the spiral arms and are thought to be amplified by a cosmic dynamo effect, where the rotation and turbulence of the interstellar medium enhance weak seed fields into galactic-scale forces. Such magnetism can even affect the propagation of cosmic rays, adding a further layer of dynamism to this already vibrant environment. Despite all its dramatic activity, the Fireworks Galaxy remains relatively isolated, part of a small group within the M101 filament, a tenuous strand in the vast cosmic web. This seclusion may partly explain its high rate of star formation, as it has retained a rich supply of cold gas over billions of years. That reservoir continues to fuel stellar fireworks, solidifying its reputation as one of the most productive star factories in our galactic neighborhood. Each supernova in this system leaves behind more than just heavy elements and expanding shock waves. It marks a transformation of the interstellar environment. The resulting shock compresses nearby gas, potentially igniting the next wave of stellar birth. This feedback loop creates a rhythm, a heartbeat of death and rebirth, echoing across thousands of light-years. This galaxy also serves as a laboratory for understanding the connection between supernova rates and galactic environments. Its abundance of Type II supernovae, those born from the collapse of massive stars, offers valuable insight into the final stages of stellar evolution. Astronomers have used this stellar system to test models of core-collapse supernova progenitors, analyzing pre-explosion imagery of doomed stars and observing the fading afterglows. Its location near the plane of the Milky Way complicates certain observations due to intervening interstellar dust, but infrared and radio telescopes have managed to penetrate the obscuration. The chemical evolution unfolding within this galactic structure reflects the continuous enrichment of its interstellar medium. Each new generation of stars forges heavier elements, carbon, oxygen, silicon, iron, within their cores, only to disperse them through explosive deaths. Spectroscopic studies of H2 regions along the spiral arms reveal metal abundance gradients, with higher concentrations toward the core. These gradients hint at gas inflows, stellar feedback, and radial mixing processes operating over cosmic timescales. The metal-rich inner zones suggest a prolonged history of star formation and recycling, while the more pristine outer arms likely point to recent accretion of primordial gas from intergalactic space. High-resolution radio observations have mapped out the galaxy's cold molecular reservoirs, primarily traced via carbon monoxide (CO) emissions. Giant molecular clouds, ranging from tens to hundreds of parsecs in size, act as stellar cradles. Within them, supersonic turbulence, magnetic tension, and localized gravitational collapse weave a dynamic tapestry that governs how efficiently stars form. Interferometric data from observatories like ALMA have resolved intricate structures inside these clouds, uncovering hierarchical clumps and filamentary strands at parsec scales. X-ray observatories, including Chandra, have revealed hot, diffuse gas filling large regions of the galactic disk, especially around recent supernova remnants. This plasma, reaching millions of kelvins, is produced by shock heating and contributes to the overall pressure balance of the interstellar medium. Together with ultraviolet and H-alpha imaging, these high-energy observations help quantify the energy feedback from massive stars, via winds, photoionization fronts, and explosions. Whether a given pocket of gas will cool and collapse into stars, or remain suspended as warm ionized material, depends on this delicate energy balance. Polarimetric observations have charted the orientation and strength of the large-scale magnetic field across this cosmic spiral. These magnetic structures not only influence cosmic ray transport but also shape the collapse of star-forming gas. Faraday rotation measures suggest coherent, ordered field lines across the disk, supporting the idea of an active galactic dynamo. The combination of spiral geometry and a rotation curve that steeply rises before flattening likely provides ideal conditions for maintaining this magnetic amplification over billions of years. The galaxy's own rotation curve has become a focal point in studies of dark matter. Observations in both optical and radio wavelengths show discrepancies between the motion of visible matter and the expected gravitational pull, pointing to an unseen mass component. Modeling the mass distribution indicates that the outer regions are dominated by a dark matter halo, whose gravity governs not only rotational dynamics but also the retention of gas and metals throughout cosmic history. Although the exact shape of this halo remains uncertain, its gravitational influence is undeniable. Recent investigations into the interstellar turbulence of this system reveal a complex, multi-phase medium in which cold molecular clouds, warm atomic hydrogen, and hot ionized gas coexist in dynamic interplay. Turbulent motions are driven by feedback from supernovae, radiation pressure, and differential rotation. Velocity power spectra indicate a cascade of energy from kiloparsec-wide flows to structures less than a parsec across, consistent with models of compressible magnetohydrodynamic turbulence. These turbulent patterns prevent collapse in some regions, while elsewhere, they foster the formation of dense filaments and clusters of stars. Out toward the galactic periphery, astronomers have detected subtle warps and asymmetries, likely remnants of tidal interactions or minor mergers. Though no major companion currently lingers nearby, telltale features in the neutral hydrogen distribution, such as extended gaseous plumes and skewed velocity fields, imply previous encounters with smaller satellites. Such interactions may have funneled fresh gas inward, triggering waves of star formation. Simulations matching the observed hydrogen kinematics show that even low-mass intruders can imprint long-lived asymmetries and generate flocculent spiral patterns, potentially explaining the broken symmetry in this galaxy's arms. The star clusters within this spiral galaxy are of particular interest. Observations from the Hubble Space Telescope have resolved hundreds of compact stellar groups, many of them both massive and remarkably young, less than 10 million years old. These clusters function as miniature laboratories of galactic evolution, where internal dynamics are influenced by mass segregation, stellar winds, and the rapid life cycle of high-mass stars. Some of these formations may evolve into long-lived globular clusters, while others will disperse into the broader stellar population. By analyzing the age and mass distribution of such clusters, astronomers can reconstruct the recent star formation timeline, revealing peaks that likely correspond to global or localized bursts. At its center lies an enigmatic nucleus. While no definitive active galactic nucleus, AGN, has been confirmed, hints of a faint nuclear source suggest low-level or intermittent accretion activity. Infrared excesses and subtle radio emissions point toward the possibility of a hidden AGN, though its energy output falls far below that of typical Seyfert galaxies. The central region also hosts a nuclear starburst ring, likely sustained by gas inflow driven by weak oval distortions in the galactic disk, an expression of slow, secular evolution. These gas flows may eventually nourish a dormant black hole, potentially reawakening central activity and illustrating the blurred boundary between passive and active nuclei. On a grander scale, this galactic system occupies a node within a sparse filament of the cosmic web. Its proximity to the zone of avoidance, partially obscured by the Milky Way, has historically complicated its inclusion in large-scale structure maps. Nevertheless, recent surveys using radio and infrared observatories have begun to unveil its surroundings, a delicate network of diffuse gas and low-mass companion galaxies. These filamentary structures trace the hidden scaffolding of dark matter and baryons, offering a window into how galaxies grow in lower-density environments, far from the gravitational violence of crowded clusters. Stellar population synthesis models reveal a composite nature, ongoing star formation layered atop a much older stellar disk. The galaxy's spectral energy distribution, covering ultraviolet to radio wavelengths, highlights both luminous blue stars and aging red giants. Integrated light measurements suggest a sustained star formation rate of around 4 to 5 solar masses per year, nearly 4 times that of the Milky Way, persisting over hundreds of millions of years. This steady activity, fed by a stable gas supply and modulated by stellar feedback, provides a useful benchmark for the study of star formation in spiral galaxies operating in a regulated, main sequence mode. Despite its elevated activity, star formation in this system follows well-established laws. Observations of carbon monoxide and neutral hydrogen, combined with H-alpha and far-infrared emissions, demonstrate a strong correlation between cold gas density and star formation rate, consistent with the Kennicutt-Schmidt relation. This implies that even in dynamic environments, star birth remains governed by predictable mechanisms. Within dense molecular clouds, gas cools via CO rotational transitions and fine-structure atomic lines, allowing gravitational collapse to proceed. However, this process is delicately balanced by local factors, pressure, turbulence, magnetic fields, and feedback from newly formed stars that inject energy and momentum into their surroundings. One of the most intriguing aspects of this galaxy is the complex interaction between different phases of the interstellar medium. Spectroscopic and photometric analyses show the presence of multiple thermal dust and gas components. Cold molecular clouds at temperatures around 10 to 20 K dominate the millimeter regime, while warmer dust grains heated to 30 to 50 K emit strongly in the mid-infrared. Ultraviolet and soft X-ray observations trace highly ionized gas in shock zones near OB associations and supernova remnants. These coexisting components underscore the ongoing exchange of energy between ISM phases, driven largely by supernova feedback and large-scale turbulence. This local spiral also plays an important comparative role in the study of galaxy evolution across cosmic time. Many galaxies observed at redshifts around Z1 to 2 exhibit clumpy, turbulent disks and irregular morphologies, shaped by rapid star formation. Although more structured and mature, the galaxy in question shares several key traits: intense stellar nurseries, elevated gas fractions, and an abundance of massive clusters, making it an excellent nearby proxy for understanding the chaotic early epochs of galactic assembly. Far-infrared observations from the Herschel and Spitzer space telescopes have yielded high-resolution maps of thermal dust emission. The dust-to-gas ratio here is relatively high, in line with both the system's metallicity and ongoing star-forming activity. Spatial distributions of cold and warm dust align closely with the spiral arms, especially in regions rich in H2 zones and youthful clusters, where ultraviolet photons from hot stars heat surrounding grains. By modeling this radiation, astronomers can estimate dust mass, grain size distributions, and the strength of the interstellar radiation field across the disk. In addition to light and gas, cosmic rays play a crucial yet often invisible role in shaping the environment of this galaxy. Radio continuum surveys at around 1.4 GHz reveal diffuse synchrotron emission, produced by relativistic electrons spiraling along magnetic field lines, that maps the distribution of cosmic rays. These high-energy particles, originating from supernova remnants and stellar winds, permeate the galactic disk. They contribute to the overall pressure balance of the interstellar medium and influence both the ionization state and chemistry of dense molecular clouds. Recent research suggests that the transport of cosmic rays is anisotropic, aligned with the spiral structure and magnetic field lines, further evidence of the intricate coupling between energetic feedback and large-scale galactic morphology. The dynamics of the spiral arms themselves have also become a subject of focused investigation. Unlike grand design spirals with continuous, symmetric arms shaped by density wave theory, this stellar system exhibits a more fragmented, flocculent structure. Such morphology is likely maintained through transient gravitational instabilities and swing amplification. Rather than static features, the arms appear to be evolving patterns, generated and dissipated through internal processes like gravitational collapse, shear flows, and stellar feedback. Numerical simulations of self-gravitating disks that replicate the patchy appearance of this galaxy support these conclusions, indicating that spiral arms can form and dissolve on timescales of approximately 100 million years, consistent with the diversity of ages seen among young clusters. Beyond the main disk, there is compelling evidence for ongoing accretion of gas from the surrounding cosmos. Deep HI mapping has detected low-density streams and filaments of hydrogen gas extending far beyond the visible stellar component, possibly the vestiges of ancient infall or minor mergers. These structures may act as slow, steady feeders of cold gas to the inner regions, sustaining star formation through so-called cold-mode accretion. This mechanism is increasingly recognized as a key factor in the long-term evolution of isolated galaxies. The presence of faint, low-surface brightness features in the galaxy's outskirts hints at a more complex history than its relatively quiet appearance suggests. Stellar streams and warped HI layers may be the remnants of disrupted dwarf satellites or diffuse gas clouds captured by the gravitational potential well. Although such features are often obscured at optical wavelengths due to foreground extinction from the Milky Way, they are becoming more accessible through deep imaging campaigns and advanced radio surveys. Their chemical composition, motion, and alignment with the surrounding gas envelope point toward an ongoing sequence of minor mergers, supporting hierarchical models of galaxy formation. This spiral galaxy also provides valuable data for probing the distribution and nature of dark matter in disk galaxies. Its rotation curve, derived from precise velocity measurements in both neutral hydrogen and carbon monoxide, exhibits the familiar discrepancy between visible mass and observed rotational dynamics. The outer regions are dominated by a dark matter halo, whose gravity not only shapes the galaxy's rotation but also influences its capacity to retain gas and metals. Attempts to fit various halo models, such as the Navarro-Frank-White profile or pseudo-isothermal distributions, offer insight into the long-standing cusp core debate. Notably, the inner portion of the rotation curve appears to favor a cored dark matter profile, perhaps shaped by energetic stellar feedback that has softened the central density over time. Adding further complexity, the large-scale magnetic architecture of this galaxy reveals coherent spiral patterns that do not always align with the luminous arms. These so-called magnetic arms, identified through radiopolarization, span the interarm regions and appear stable over tens to hundreds of millions of years. Their structure is likely maintained by a mean field dynamo process, where the interplay between differential rotation and turbulence within the disk amplifies and organizes the magnetic field. These fields, in turn, regulate gas dynamics by guiding flows, resisting fragmentation, and applying pressure that can counterbalance gravitational collapse, thereby shaping when and where stars can form. The galactic center, though lacking a classical active nucleus, may nonetheless harbor a low-mass black hole nestled within a dense nuclear star cluster. Near-infrared spectroscopic surveys have identified central peaks in velocity dispersion, possibly indicative of a dynamically hot stellar population or the gravitational pull of a compact object. Due to dust obscuration and the absence of broadline features, estimating the black hole's mass is challenging. However, dynamical modeling places its upper limit at a few million solar masses. If confirmed, such a central black hole would occupy the lower end of the black hole mass-bulge mass relation, offering valuable insight into black hole formation in late-type spiral galaxies. The intricate interplay of components in this system, stars, gas, dust, dark matter, magnetic fields, and cosmic rays, illustrates the complexity of galactic ecosystems. Each constituent shapes and is shaped by the others. Stars enrich the interstellar medium, magnetic fields direct the flow of gas, dark matter governs large-scale dynamics, and supernovae inject energy that regulates temperature, structure, and further star formation. Feedback loops within the disk are both limiting and generative, maintaining a high but stable rate of stellar birth while preventing rapid depletion of gas supplies. This galaxy also acts as a cosmic observatory, offering astronomers real-time access to the full stellar life cycle. Its record-breaking number of observed supernovae, such as SN 2004 ET and SN 2017 E, provides exceptional case studies of massive star death, from pre-explosion imaging to fading remnants. These events refine models of progenitor structure, nucleosynthesis yields, and the physics of supernova remnants. Intriguingly, some massive stars in this galaxy have simply vanished without producing a visible supernova, raising the possibility of failed explosions leading directly to black hole formation. One particularly notable case is that of N6946, BH1, a luminous red supergiant initially estimated at 25 solar masses, which dimmed and disappeared from optical view. The absence of an accompanying bright explosion, coupled with faint lingering infrared emission, points toward a quiet gravitational collapse, possibly forming a black hole through fallback accretion. If verified, such events could represent a significant, undercounted population of stellar deaths, bypassing the traditional supernova route. This challenges existing models of core collapse, especially in regard to the influence of rotation, magnetic fields, and neutrino physics. The chemical composition of the interstellar medium offers another window into the galaxy's past. Spectroscopic mapping of H2 regions reveals clear radial gradients in elements like oxygen, nitrogen, and sulfur, typically decreasing with distance from the center. However, deviations from this trend, such as localized metallicity plateaus or sudden drops, may indicate recent infall of metal-poor gas, incomplete mixing, or spatial variations in star formation history. These chemical signatures allow astronomers to trace feedback-driven fountain flows, episodic gas accretion, or the radial migration of stars across the disk. Radial migration, in particular, plays a key role in shaping the distribution of stellar populations over time. Caused by interactions with transient spiral arms or weak bar-like distortions, stars can move significantly inward or outward while preserving near-circular orbits. This migration blurs the classical age, metallicity, radius relationships and complicates attempts to reconstruct galactic history, but it also explains how the outer disk can contain old stars that originally formed in the inner regions. Such redistribution contributes to the development of extended ultraviolet disks and thick stellar components. In terms of triggering star formation, this spiral galaxy exhibits a variety of mechanisms. In addition to large-scale instabilities and spiral arm compression, there is evidence for self-propagating star formation. Observations reveal sequences of star-forming regions aligned along expanding shells, likely caused by pressure waves from earlier generations of stars. These waves compress nearby gas, initiating new bursts of star formation in a cascading fashion. The resulting stellar complexes and molecular clouds exhibit hierarchical, fractal-like structures. These patterns are supported by scaling relations between cloud size and velocity dispersion, consistent with turbulent cascade models of the interstellar medium, the cold dust component, traced by submillimeter observations from SCUBA and Herschel Spire, also reveals temperature and opacity variations across the disk. These properties are sensitive to grain size distributions, coagulation processes, and the local radiation field intensity. Dust grains play a critical role in shielding molecular gas, catalyzing the formation of H2 on their surfaces, and regulating the thermal balance of star-forming regions. Variations in the dust-to-gas ratio across the disk of NGC 6946 are tied to its metallicity gradient, with lower dust content in the outskirts and higher concentrations near the center. Radiative transfer models applied to the full spectral energy distribution, SED, help disentangle these effects and reconstruct the three-dimensional dust structure. On galactic scales, NGC 6946 exhibits signs of secular evolution, slow, internal processes that reshape its structure over billions of years. The lack of a strong central bar, but the presence of weak oval distortions and an asymmetric stellar distribution, suggest that internal torques are redistributing angular momentum. This, in turn, channels gas inward, sustaining the central starburst and potentially building a pseudobulge, a structure formed not by violent mergers, but by steady inward flow of disk material. Observations of stellar kinematics and photometric decomposition support the presence of such a component, with intermediate scale heights and enhanced alpha element abundances indicating rapid past enrichment. NGC 6946, then, stands as a vibrant, evolving ecosystem, an archetype of a gas-rich spiral undergoing sustained star formation and self-regulation. Its value to astrophysics lies not just in its photogenic appearance or prolific supernova rate, but in the way it encapsulates a diverse range of physical processes, from turbulence and magnetism to feedback and secular dynamics. It bridges the gap between local, well-resolved systems and distant, unresolved galaxies observed in the early universe, providing the empirical grounding necessary for testing and refining cosmological models of galaxy formation and evolution. In recent years, integral field spectroscopy, IFS, has become a transformative tool for studying galaxies like NGC 6946, offering spatially resolved maps of kinematic and chemical properties across the disk. Instruments such as MUSE, Multi-Unit Spectroscopic Explorer, and KCWI, Keck Cosmic Web Imager, enable astronomers to construct full 3D data cubes, capturing spectra at each pixel and revealing the internal motions of stars and gas in exquisite detail. For NGC 6946, such observations have shown that the velocity dispersion of ionized gas increases in the inner regions, likely due to turbulence from stellar feedback and central mass concentration. Meanwhile, stellar motions reveal a dynamically colder thin disk and a thicker, older population with higher vertical velocity dispersion, indicating layered components built up over time. Molecular gas kinematics observed with interferometers like ALMA and NOMA show that gas in star-forming regions often exhibits signs of non-circular motion, such as inflows, streaming along spiral arms, or localized outflows. These motions, when compared with gravitational potential models, suggest that the gas does not merely orbit passively but is dynamically active, flowing along pressure and gravitational gradients shaped by feedback, spiral perturbations, and possibly past tidal interactions. These complex flows help drive gas toward central regions, where it feeds nuclear star formation and potentially builds mass concentrations. Furthermore, NGC 6946 exhibits localized superbubbles, large cavities in the interstellar medium blown by clusters of massive stars. These bubbles, several hundred parsecs in diameter, are observable in H-alpha and X-ray maps, where they appear as shell-like structures surrounding diffuse hot gas. Some of these superbubbles coincide with past supernova remnants and are thought to have expanded due to overlapping shock fronts from multiple explosions. These structures can puncture the galactic disk, driving hot gas into the halo and forming galactic fountains, where enriched material is expelled from the plane and later cools and falls back, helping to mix the interstellar medium and redistribute metals over large scales. NGC 6946's extended HI disk, mapped with single-dish and interferometric arrays, shows that neutral hydrogen stretches well beyond the optical disk, up to more than 50 kpc in diameter. This vast, low-density component rotates more slowly and contains several asymmetries and warps, suggesting ongoing interaction with the surrounding intergalactic medium. Such extended HI structures are key indicators of external gas accretion, and their kinematics can trace the shape and orientation of the dark matter halo far beyond what stellar motions reveal. The flattening and stability of the HI disk over such scales also provide constraints on the total mass distribution and the potential triaxiality of the dark matter halo. Studies of resolved stellar populations in this galaxy, using ultraviolet and near-infrared imaging from the Hubble Space Telescope, have revealed age gradients and color magnitude diagrams indicative of continuous star formation spanning several gigayears. Its disk is home to a diverse stellar population, ranging from young, luminous blue stars in clusters to evolved red giants and asymptotic giant branch stars. This range of ages and compositions enables astronomers to reconstruct the galaxy's star formation history at fine spatial scales, revealing patterns of episodic bursts, intervening quiet periods, and radial stellar migration. In some peripheral regions, the presence of unexpectedly young stars suggests rejuvenation events, likely triggered by infalling gas or the outward extension of spiral arms into previously quiescent zones. On a broader cosmological stage, this system's position near the zone of avoidance, where the dense plane of the Milky Way obscures extragalactic views, makes it a key anchor for tracing the structure of the local universe. Velocity measurements and HI distribution studies confirm that it belongs to a sparse filamentary network connected to the M101 group. These filaments are not simply visual alignments but dynamically evolving structures molded by the gravitational scaffolding of the cosmic web. Investigating galaxies embedded in such filaments helps clarify how environmental factors, like gas accretion, merger frequency, and angular momentum acquisition, shape galactic evolution across cosmic time. This stellar system also plays a pivotal role in advancing theories of feedback-regulated star formation, a central element in galaxy formation models. The interplay between energy injection from young stars, via radiation, stellar winds, and supernovae, and the cooling and condensation of gas determines whether a galaxy continues to form stars or becomes quenched. In this case, star formation proceeds at a high yet self-regulated pace, suggesting a quasi-equilibrium state where feedback maintains sufficient turbulence and pressure to prevent catastrophic collapse while still allowing steady stellar production. Such a balance aligns well with predictions from cosmological simulations like EAGLE and Illustris TNG, which aim to reproduce the diversity of galaxy types through detailed modeling of baryonic physics. Ultimately, this galaxy is far more than a supernova hotspot or a visually captivating spiral. It serves as a richly structured, chemically evolving, magnetically ordered, and energetically self-regulating galactic ecosystem. It bridges the scales between stellar physics and the cosmic web, offering a unique window into how local processes interweave with the broader narrative of the universe. Through it, one can trace the mechanics, the cycles, and even the poetry of cosmic evolution. The galaxy's prominence as a star-forming engine is also underscored by its intense infrared luminosity. Observations from space telescopes such as Spitzer and Herschel have mapped the far-infrared glow from dust grains heated by ultraviolet and optical radiation. This places the galaxy near the threshold of the luminous infrared galaxy, LIRG, category, an impressive feat given its moderate mass and lack of major companions. The spectral energy distribution, SED, reveals multiple dust temperature components, with cooler dust in the outskirts and warmer regions concentrated in compact starburst zones. These thermal signatures allow for detailed modeling of dust grain composition, such as silicates and carbonaceous species, and their size distributions, which are shaped by processes like sputtering, coagulation, and photodestruction. On the molecular scale, high-resolution measurements of rare CO isotopologues like superscript 1 superscript 3 CO and C superscript 10 provide insight into the temperature and density structure within giant molecular clouds. These lines penetrate deeper into dense regions than standard CO transitions and help disentangle radiative transfer effects. The observations reveal that many clouds are clumpy, filamentary, and internally structured, with compact dense cores embedded in diffuse envelopes. This supports the idea that star formation follows a hierarchical, self-similar pattern. Shock tracers such as CO and high-density tracers like HCN and HCO further illuminate the conditions required for massive cluster formation within these clouds. The galactic magnetic field subtly shapes many of these processes. Synchrotron emission maps from polarized radio data show that both ordered and turbulent magnetic field components are present. The ordered fields often align with spiral structures and persist even between arms, while the turbulent components correlate strongly with sites of active star formation and supernova feedback. The coherence of the regular field across kiloparsec scales points to an active large-scale alpha-omega dynamo, maintained by differential rotation and mirror asymmetric turbulence. These magnetic structures influence angular momentum transfer, guide gas flows, and even affect the fragmentation of collapsing clouds, potentially shaping the initial mass function, IMF, of new stars. In the time-domain frontier, this galaxy has proven indispensable. Its high rate of core collapse supernovae provides a unique laboratory for comparing light curves, explosion mechanisms, and progenitor environments under consistent galactic conditions. Events like SN 2004 ET and SN 2017 E have been monitored in detail across the electromagnetic spectrum, offering valuable data for modeling shock physics, dust formation, and energy transport. Some of these supernovae have even produced light echoes, reflections of their light off interstellar dust, which enable three-dimensional reconstructions of the surrounding medium. These echoes reveal not only the nature of the explosions but also the small-scale structure and composition of the interstellar environment itself. Meanwhile, theoretical models continue to advance in parallel with observational insights. State-of-the-art hydrodynamical simulations, now incorporating feedback from massive stars, cosmic ray pressure, magnetic field dynamics, and realistic cooling functions, are capable of reproducing many of this galaxy's key features, from its patchy, flocculent spiral arms to its chemical gradients and regulated star formation activity. These results support the view that systems like this one represent a point of dynamic equilibrium, where energy feedback ensures structural stability, accretion maintains star-forming material, and internal processes build complexity without the need for major external perturbations. Beyond its own borders, this nearby spiral acts as a Rosetta Stone for interpreting galaxies in the distant universe. The clumpy, gas-rich disks seen at redshifts around Z1 to 2 often resemble scaled-up versions of this system. Its internal regulation, feedback cycles, and multi-phase interstellar medium provide a blueprint for interpreting less resolved galaxies in the early cosmos. In this sense, the so-called fireworks galaxy forms a bridge between the local universe and the formative epochs of galactic assembly. Its scientific legacy is thus multifaceted. It is a prolific supernova laboratory, a magnetically structured dynamo, a chemically complex feedback system, and a living fossil of secular galactic evolution. Every aspect, from its turbulent disk and star-forming rings to its coherent magnetic arms and diffuse halo, contributes to our understanding of how galaxies evolve, recycle, and interact with the cosmic environment. The photons that reach Earth after traveling over 22 million years carry not just images, but the imprints of stellar birth, death, and renewal. To observe this galaxy is to witness a chapter in the ongoing chronicle of cosmic evolution, written in light, gas, and gravity. Among the most revealing aspects of this narrative is the role of chemical feedback. Each stellar generation, particularly massive stars, contributes to the galactic ecosystem by returning the byproducts of nucleosynthesis to the interstellar medium. Elements such as oxygen, magnesium, and iron, forged in stellar cores and expelled in supernovae, enrich the surrounding gas, seeding future star formation. Thanks to the unusually high frequency of stellar explosions, this galaxy offers an ideal environment for studying how these enrichment cycles unfold across space and time. Detailed maps of abundance ratios like O/Fe and C/S reveal that chemical feedback is often localized, shaped by the type of progenitor and the dynamics of the receiving medium. Some zones retain stratified elemental layers, others show turbulent mixing likely driven by shear flows and convective instabilities. These variations serve as calibration points for galactic chemical evolution models, shedding light on the formation of metallicity gradients and the temporal evolution of the interstellar composition. Dust grains, formed in AGB stars and supernova remnants, add further richness to the chemical story. These particles are not mere bystanders, they shape the thermal physics and chemistry of molecular clouds, regulate star formation via shielding, and act as surfaces for complex molecule formation. Over time, grains are modified by radiation, shocks, and grain-grain interactions, altering their size distribution and composition. In this galaxy, observations of silicate absorption near 9.7 micrometers and polycyclic aromatic hydrocarbon (PAH) emissions around 8 to 12 micrometers show regional variation that traces both environmental conditions and the life cycles of dust itself. PAHs, for instance, flourish in quiet interarm regions but are destroyed near OB clusters, illustrating a delicate balance between dust survival and stellar radiation. Another emerging frontier lies in the galaxy's vertical structure. Faint H-alpha emission reveals a warm, diffuse ionized gas layer, an extraplanar component that rises several kiloparsecs above the galactic midplane. Supported by turbulent and thermal pressure, this EDIG halo may be driven by supernova-powered superbubbles or galactic fountain flows, gradually building up a chemically enriched halo. Such a structure resembles the circumgalactic medium seen in larger systems and may represent its early phase, already influencing the galaxy's baryon cycle. Cosmic rays also play an increasingly recognized role in sculpting this vertical environment. Relativistic electrons accelerated by supernova shocks escape into the halo, where they trace out large-scale magnetic loops and contribute to synchrotron emission detected at radio frequencies. Vertical gradients in radio continuum brightness suggest that these particles diffuse and advect over kiloparsec scale distances. The resulting winds, though weak compared to those in starburst galaxies, may be sufficient to lift both gas and magnetic fields into the halo, enriching the surrounding medium and sustaining low-level outflows. Even in the absence of an active galactic nucleus, taken as a whole, this luminous spiral stands as a vivid example of how galaxies are not static star catalogs or gas reservoirs, but dynamic, self-regulating engines of cosmic change. Its arms are not just architectural flourishes, but gravitational wavefronts sweeping through the disk, sculpting matter, igniting starbursts, and imprinting enduring patterns of chemistry, radiation, and magnetism long after the light of young stars fades. Its nucleus, far from inert, is a site of subtle flows, hidden mass, and enriched complexity. And its surrounding halo, often assumed empty, is in fact a quiet archive, accumulating light, metals, and memory through outflows and fountains. To observe such a galaxy is to read an unfinished manuscript of cosmic evolution, each supernova a punctuation mark, each filament of gas a narrative thread, each photon a whisper from the past. Its stellar population encodes its origins, its gas and dust trace its present processes, and its spiral choreography hints at a future written in feedback, entropy, and gravitational order. Its role as a cosmic archetype even extends into the high-energy domain. Beyond the visible and infrared glow, this system produces a faint yet meaningful background of X-ray emission, traced to the aftermath of powerful events and compact stellar remnants. Observations from telescopes like Chandra and XMM Newton have uncovered dozens of point sources embedded within its disk, many identified as high-mass X-ray binaries, systems where neutron stars or black holes feed on the winds of massive companions. These luminous pairs are direct legacies of recent star formation and act as cosmic chronometers, their presence marking the time since massive stars first ignited. The luminosity function of these X-ray sources follows a characteristic power law seen in other star-forming systems, suggesting the presence of universal accretion physics across galaxies. Some of the brightest sources may be ultraluminous X-ray emitters, ULXs, enigmatic objects whose output surpasses the Eddington limit for stellar mass black holes. These may harbor intermediate mass black holes or manifest extreme accretion geometries with beaming or disk instabilities. This galaxy's X-ray population provides a window into such exotic regimes, linking compact object evolution to stellar feedback and metallicity. Even at gamma-ray energies, though currently below detection thresholds, theoretical models predict emissions from cosmic ray interactions within the interstellar medium. Collisions between relativistic protons and ambient gas create neutral pions, which decay into gamma photons. While current instruments lack the sensitivity to fully resolve this emission from the fireworks galaxy, future observatories such as the Cherenkov Telescope Array, CTA, may probe these processes directly, offering insight into how ordinary spiral galaxies like this one accelerate and confine cosmic rays over millions of years. One of the most compelling frontiers now emerging is the relationship between the galaxy's magnetic architecture and its dynamo history. Theories of galactic magnetic field generation suggest that strong turbulence and rapid rotation in young galaxies drive field amplification through a turbulent dynamo. Over time, these chaotic fields coalesce into coherent, large-scale structures. With its mix of ordered magnetism and active turbulence, this system may occupy a transitional state in that evolutionary path. Using Faraday tomography, where polarized radio waves reveal magnetic field geometry through frequency-dependent rotation, astronomers can now reconstruct the three-dimensional magnetic topography of its disk. These maps unveil the pitch angles, reversals, and helicities of field lines, directly comparing real data to the predictions of galactic dynamo theory. Its structure reveals tight spiral arms filled with pinkish hydrogen emission regions, H2 zones, glowing from ultraviolet radiation emitted by newborn stars. These stellar nurseries are teeming with protostars, each a pocket of cosmic creation. Dust lanes, visible in infrared, weave through the galactic disk like shadowed brushstrokes on a canvas. When viewed across the electromagnetic spectrum, from radio to X-rays, this system emerges as a chaotic yet harmonious symphony of gas flows, magnetic fields, and stellar winds. At its core lies a site of intense star formation, emitting powerfully in the far infrared, heated by ultraviolet light absorbed by interstellar dust. Unlike grand design spirals with defined bulges or bars, this central region is soft, turbulent, and asymmetric, perhaps the consequence of past mergers or gravitational interactions with smaller companions now dissolved into its halo. Observations have revealed strong magnetic fields, threading through the arms and amplified by a galactic dynamo effect. These fields not only shape gas motion but influence cosmic ray propagation, adding depth to the galaxy's already dynamic nature. Despite its activity, this spiral remains relatively isolated, part of a sparse group within the M101 filament. Its seclusion, paired with a vast cold gas reservoir, may help explain its high star formation rate. Each supernova does more than expel heavy elements, it triggers the next wave of stellar birth, creating a heartbeat of death and rebirth echoing across thousands of light-years. This galaxy serves as a cosmic lab for understanding stellar death and chemical enrichment. With a record number of Type II supernovae, astronomers have traced their progenitors, observed fading afterglows, and tested core collapse models. Spectroscopy reveals metallicity gradients in its arms, higher near the center, indicating long-term enrichment and radial mixing. Molecular gas traced by CO emissions appears in vast, turbulent clouds that give rise to stars through gravitational collapse. X-ray and ultraviolet observations expose hot, diffuse plasma surrounding recent supernova activity. These regions mark the boundaries between gas phases, some condensing into stars, others suspended in ionized states by stellar winds and radiation. Radiopolarization maps reveal a well-structured magnetic field, not only guiding cosmic rays but potentially regulating star formation and stabilizing interstellar clouds. The galaxy's rotation curve further implicates the presence of dark matter. Discrepancies between visible mass and orbital speed suggest a dominant halo, especially beyond the optical disk. Mass models favor a chord profile, potentially sculpted by baryonic feedback. Observations of warps, HIA symmetries, and faint stellar streams point to past minor mergers and continued gas accretion, likely feeding the galaxy's inner regions and maintaining its vitality. The galaxy's flocculent arms, unlike the grand spirals of M51, are likely maintained by internal dynamics, swing amplification, feedback loops, and turbulence, rather than density waves. These arms form, dissolve, and reform in transient rhythms, illustrating a self-organizing system rich in molecular gas and relatively free from external disturbance. Beyond the visible disk, faint extraplanar H-alpha emission suggests the presence of a warm, diffuse ionized gas halo. Superbubble blowouts and galactic fountains lift enriched gas into this extended region, slowly building a chemically rich circumgalactic medium. Relativistic particles traced by synchrotron radiation extend several kiloparsecs above the disk, suggesting that even without a central AGN, the galaxy produces mild winds that lift gas, dust, and magnetic fields into the halo. In the infrared, dust heated by massive stars glows brightly. Spitzer and Herschel observations place this system near the threshold of luminous infrared galaxies, LIRGs. Its spectral energy distribution reveals multiple dust temperatures and compositions, shaped by sputtering, radiation, and grain collisions. Dust not only reprocesses starlight but also acts as a catalyst for molecular chemistry and star formation. Dust is further shaped by local conditions. PAHs and silicate features vary across the disk, strong in interarm regions, destroyed in intense star-forming zones. This interplay between radiation and dust grain evolution offers a microphysical view into how galaxies recycle matter and light. The nuclear region may harbor a low-mass black hole hidden within a nuclear star cluster. Velocity dispersion peaks and faint infrared signals hint at such a presence, placing it on the low end of the black hole bulge-mass relation. If confirmed, this compact object adds another piece to the puzzle of black hole formation in late-type spirals. Radial migration, where stars shift outward or inward without significantly altering their orbits, helps explain how the outer disk can host older stars that originally formed near the core. This redistribution complicates efforts to trace chemical evolution but also contributes to the formation of thick disks and extended UV structures. The Fireworks Galaxy is also a rich time-domain laboratory. Supernovae like SN 2004 ET and SN 2017 E have been observed across the electromagnetic spectrum, providing insight into explosion dynamics, nucleosynthesis, and dust formation. Light echoes reflected from surrounding dust even enable 3D reconstructions of the interstellar environment. High-energy emissions from X-ray binaries further trace recent star formation. Some sources may be ULXs, candidates for intermediate-mass black holes or exotic accretion states. Gamma-ray emissions from cosmic ray interactions remain undetected but may become visible with future observatories like the CTA. The galaxy's magnetic fields, both ordered and random, play an invisible but essential role. They align with spiral arms, thread through interarm space, and may help maintain arm structure in tandem with gravity and turbulence. Polarized far-infrared emission reveals their interaction with aligned dust grains, observable by missions like SOFIA and future JWST successors. Such magnetic fields are not isolated phenomena. They are woven into the ISM itself, shaping accretion flows, collimating outflows, and influencing the spatial coherence of the disk. Faraday tomography techniques are beginning to map their 3D geometry, offering insight into pitch angles, helicity, and the operation of large-scale dynamo processes. Simulations now replicate many of the galaxy's observed properties, morphology, metallicity, and regulated star formation, by including magnetic fields, feedback, and cosmic rays. These models suggest that the fireworks galaxy exemplifies an equilibrium point in galactic evolution. Feedback maintains order, accretion sustains growth, and internal processes shape structure. Looking forward, its evolution may follow a familiar arc. If star formation continues at current rates, it will eventually consume its molecular gas. Yet, signs of outer disk accretion suggest that quiescence is still far off. Over billions of years, it may transition into a more lenticular form, spiral arms fading, supernovae waning, and stellar populations aging into red stillness. But its chemical fingerprints, stratified halo, and magnetic spirals will remain, fossil records of a more active past. In this way, the fireworks galaxy embodies the life cycle of galactic systems. It is not static, not passive, but alive with formation, feedback, and transformation. Its spiral arms are currents of gravitational choreography, its supernovae, punctuation in a cosmic manuscript. It is a galaxy in motion, threaded with invisible forces and radiant with stories written in light and time. Every wavelength we observe adds another page, cold gas poised to collapse, warm dust glowing from stellar birth, hot plasma rushing through blown-out cavities, and ancient stars whispering of epochs gone. This is no simple object, it is a galactic chronicle, unfolding across millions of years. As our instruments sharpen and theories deepen, this nearby spiral continues to reveal new layers of meaning. It stands as a luminous bridge between what we can resolve and what we only imagine. And in the silence of space, it speaks in a language of energy and order, a language we are just beginning to understand. To gaze upon this galaxy is to look into the past, and into the very mechanisms that shape the future of galaxies like our own. It reminds us that the universe is not still, not quiet, but alive with motion. And in that motion, we glimpse the rhythm of the cosmos, subtle, relentless, and beautiful.